Welcome to ourbiostatistics.com. So today I'll be talking about distribution and more importantly normal distribution and how to test for it. So what distribution is essentially how our data will look when we plot it on, say, histogram or a frequency distribution graph, is the shape that it takes. There are many different types of distribution. Our data can have many different shapes, but one that we're particularly interested in statistics is normal distribution, also known as Gaussian or bell-shaped distribution, and is ubiquitous in nature, is very, very common, and is one that will have a big impact on, or has a big importance in statistics, and is important because some tests will require you to know that your data is normally distributed before you can perform them. Examples such as the t-test or ANOVA will require you to know that your data is normally distributed before you can use them. So therefore, looking at the distribution of our data as a first step in statistical analysis is something that is often a very good thing to do, and I'll show you how to do it on ourbiostatistics.com now. So if you navigate to the descriptive tests and select distribution, there will be a dataset available to you. You can click Analyze. And then the dataset is in an Excel format, so we can just choose Excel and select our dataset. Okay, so here we'll be looking at the height of 100 students, 100 university students, and then we'll talk about this second column a bit later on. So we can then select our variable, in this case height. It will show up on our selected column, and then we'll perform something called a one sample Kolmogorov Smirnov test. So essentially, what we can do when looking at distribution is, more crudely, is have a look at the histogram. And this is a histogram of the distribution of our data, and as we can see, it looks normally distributed. But this is a very crude method, and the one sample KS test will give us a statistical likelihood that our data is normally distributed. So what the KS test does is compare the distribution of our data to a perfect normal distribution, and it will then tell us the likelihood that our data is significantly different from that perfect distribution, normal distribution, or if it is similar to that normal distribution. So this is the output from the KS test, and the first important number that we're going to be looking at is the D value, which is known as the test statistic, and this is how different our distribution is to a normal distribution. So this is also known as divergence. In this case, the higher the value is, the less likely it is that our data is normally distributed. So you want this value to be very low. Now, the p-value, on the other hand, it statistically quantifies the probability that the divergence between our data and normal distribution is not caused by mere chance. So essentially, in this case, the lower the p-value, the less likely our data is to be normally distributed. So in summary, a very low test statistic, or D value, and a very high p-value, like in this case, suggests that this is normally distributed. As you can see, the p-value is not statistically significant, is not below the 0.05 threshold. So we can safely assume that our data, our height data, is normally distributed. Now, let's have a look at a set of data that is not normally distributed. So in this case, we'll have a look at the number of surgeries a group of 100 students underwent in their lifetime. So we can unselect height and select surgery as our value, and hopefully it'll show up in our selected columns. There we go. And then if we have a look at the histogram, first of all, we can see that this is not normally, it doesn't look normally distributed. It's heavily skewed to the left. And if we look at our KS test, that will show us that our D value is much, much higher than before. And our P value is much, much lower than before. In fact, it is very, very significant. So all in all, this shows us that this data set is not normally distributed. So that's all I want to tell you about distribution. Thank you very much for listening.